Let's go back and look at the earlier design decisions from the point of view of pile driving. First, the decision that what we want to do is to drive a pile. Were we to write this function out using the longer form, we would say that we want to change the position of the pile with relation to the top of the ground by pushing it into the ground. We could have said other things like bury the pile, but we chose to drive it. Next, we decided that we wanted to drive the pile using the phenomenon of mechanical stress resulting from impact or vibration. Next, we decided that the objects would be a pile driver, and the earth. The earth and pile are necessary elements in the system. The driver is not a required element. For instance, if there were native resources that could have driven the pile, we could have chosen those. If you want to know more about using native resources, go to the ebook Idealizing Useful Functions. Next, we decided that the starting architecture would be the pile driver driving the pile from above into the earth below. The pile guides the pile driver rod to make sure that each impact occurs with precision. Note that I said starting architecture. The following decisions may affect this architecture. Next, we decided we wanted to improve the driving speed. Now we have to determine what the parameters are that affect the driving speed. We use experience and modeling to understand what the important parameters are. I realize that many of those watching will not know how to model this system. An understanding of physics and how to model such problems will allow the product developer to develop a wider range of products. On the other hand, I realize there are many that do not have this training. So what can they do? They can handle this by gaining experience from simple prototypes and experiments. Even if you think you know the physics, experiments will teach a lot. Shown here are what are called free body diagrams of the pile driver and the earth. The pile driver strikes a pile and uses its momentum to create a very high force on the top of the pile. This force is primarily determined by two things: the mass or weight of the driver and the velocity when it strikes the pile. The frequency of striking the pile will also determine the overall speed of driver. The faster that we recover the hammer and hit the pile again, the faster it goes in. It is also possible to time the striking of the pile if it is done fast enough to make the pile resonate, thus growing in energy and driving speed. Not all of the force or energy of the pile that goes into the top reaches the bottom of the pile. If the mass or weight of the pile is too high, a lot of the energy is used up in accelerating the pile itself. This is a lot like the trick where someone with a sledgehammer strikes a rock on somebody's stomach without causing harm. Also, what is known as the spring rate or stiffness of the pile has a lot to do with the pile resonance, or the force that reaches the tip of the pile. The spring rate or stiffness is how much the pile compresses when a force is applied at the top. If the pile is very stiff, a lot more of the force reaches the tip of the pile. Next, the ground exerts a pressure at the tip of the pile. This pressure times the cross-sectional area of the pile is a resisting force that slows the pile as it drives into the ground. The pressure at the tip is controlled by the sharpness or tip angle of the pile. Moving the soil sidewards rather than downwards requires less pressure, especially closer to the surface. That is why a sharp tip angle makes the driving faster. The force pushing back from the ground is greatly reduced. Finally, the compressibility and the density of the earth itself plays an important role in how fast the pile can be driven. We don't have much control over these parameters, so we won't show them here. Let's look at the next decision, which is, what can we change to make the pile drive faster? What are the parameters that we have control over? Increasing the mass of the pile driver, the striking velocity of the pile, and the frequency of striking the pile would make it drive faster. Those three together constitute the energy that's going into the pile driver. If we increase this energy, we can drive faster. If we were renting the pile driver, then we could ask for a higher energy driver to drive faster. Going to a higher energy driver has its own problems and contradictions related to pile breakage and cost. We could also increase the stiffness of the pile. This would be done by changing the pile structure and materials. This has its own problems and contradictions, mostly related to cost. We could decrease the pile diameter. This reduces the area that the ground pressure operates and allows the pile to go in much easier. Again, this has some very obvious problems and contradictions related to pile breakage and the ability to support a heavy structure. We could decrease the mass of the pile by changing its structure and materials. This has problems and conditions related to cost and durability of the piles. Finally, we come to the tip angle, which we would like to decrease to make it sharper. We have noted that while improving the driving speed, the problem that the support of the structures on top are worse during an earthquake. This is the knob or parameter that we chose to change in order to drive faster. We could have chosen other parameters and would be faced with different problems and contradictions than the one we have chosen. Going back to these later allows us to look at more solutions. There are many ways to fry an egg. Each way provides a branching set of solutions. Most of the time when we design, we don't think of how parameters like sharpness are going to be distributed in time, space, direction, by scale, etc. We just visualize the sharpness at one point in time, in one place, at one scale, in one direction. It takes more effort to visualize the distribution, but that is exactly what we are going to do when we resolve the contradiction. The final decision is how this parameter of sharpness is going to be distributed. This is where we are now with our problem and how we got to the contradiction. As we look back over the design decisions, please realize that the earliest decisions had the most impact, especially on the cost of driving piles. However, the courage to make high-risk decisions earlier in the design process depends largely on our confidence that we have to be able to solve the problems that arise. That is why the skill of resolving contradictions is so important and probably the first that needs to be mastered.